So my name is David Brazdil. I work for Google on the Android team. I run the Android virtualization team under Android Platform Security. But today I won't be talking about that. You can see that talk from Plumbers from last year. Today I picked a slightly niche topic, maybe not perfectly relevant to everyone, but on the other hand, there's so many things happening in AOSP, and they're not typically very well advertised or documented. So I thought might be interesting to some people to at least know that this kind of stuff is happening. So the topic is RPC Binder and how to use AIDL in distributed systems. And just to begin with, I'm going to give a very quick overview of what is Binder and AIDL, in case people aren't familiar. So Android relies very heavily on interprocess communication, IPC, and the main mechanism for IPC in Android is Binder. You can find instances of Unix domain sockets being used here and there, I think especially in Zygote, but by far Binder is the main mechanism for IPC. It's also where we enforce permissions, because Binder gives you methods for reliably telling who's on the other end of a communication channel. But Binder is a slightly overloaded term. So when people say Binder, they could mean the kernel driver in Linux that is then exposed through the dev binder dev node. It's actually upstream. It's been for a very long time. And the driver facilitates exchange of buffers and file descriptors between processes. It's object aware. It can provide reference counting. It can send notifications about objects dying. And it's actually integrated with the scheduler to minimize latency. It can give hints to the scheduler that a particular process should be scheduled. Another meaning of Binder could be the libbinder shared library that each client needs to load. And then each client opens the dev binder file and starts a thread pool where each thread is waiting for events from the kernel driver. Libbinder is also where the wire format for transactions is implemented. But by definition, by design, this is not stable. This has been part of the Binder mantra from the very beginning, that wire formats should not be stabilized, and it allows to innovate over time. On top of libbinder sits the Android interface definition language, AIDL, which has a Java-like syntax for defining interfaces, and it's tightly coupled with a serialization mechanism called parserable. It's very similar to the serialization mechanism you have in Java, but it's its own thing. There's an AIDL tool which generates code bindings for Java, C++, and Rust. So all you do is you define your interface in AIDL, and then the AIDL tool will generate libraries that you can link into your own application to be able to either implement the class itself or call the interface from the caller. And the final thing the final meaning of Binder can actually be this whole concept of a remotely executable object. So if you look at the right-hand side, the diagram here, which is heavily simplified, probably wrong, but the main concept is you have a caller who can invoke a method on the so-called proxy class. This implements the AIDL interface, and when you call the proxy method, first this request is serialized using the parserable framework functions, and then it goes down to the binder transaction methods, where it's actually converted to the wire format that Binder understands, and then goes through the IPC thread state transact to the dev binder kernel module. On the other side, it's deserialized until it hits this stub class, which is just an abstract Java class that somebody needs to implement. And the actual implementation is called a native class. So this is the basic binder AIDL concept, and it's been hugely successful. It's used for defining interfaces on all levels of the stack, all the way from HALs up to applications. And for example, treble would not have been possible without AIDL and binder. On the other hand, binder is technically just an implementation detail. Clients never interact with binder directly. They always interact with these AIDL generated classes at the top, and everything else is hidden underneath and abstracted away. So AIDL is successful, and we want to use it in as many places as possible. But at some point, we're going to start hitting the limits of what binder underneath can actually do. So first of all, binder requires both clients to be running on top of the same kernel, obviously, which wouldn't work if the two clients were not running on the same kernel, like being on two different devices. And it also requires that the clients are using the exact same libbinder shared library. That's because of the unstable wire format that I mentioned earlier. So that doesn't work if the two clients are independently updated, or the libbinder library that they're using. And normally that's not a problem on Android because they all open the same SO from the system. But if they were running on different devices, then the libbinder SO versions may get out of sync. So one potential solution would be to just abandon AIDL and use gRPC with protobuf. But it's not ideal because it would lead to fragmentation in how we define interfaces. It would prevent us from reusing the existing AIDL interfaces in the system. And there's actually a lot of them. If you just look at code search for Android, there's something like 20,000 AIDL files in AOSP alone. So it's a huge library of stable interfaces that have been implemented in the past. They work really well, and we want to be able to reuse. So this is where RPC Binder comes in. It's a new abstraction to enable implementation of transports other than the kernel driver dev binder. Right? So if you look at this diagram on the right, at the bottom, we have this IPC thread state class talking to dev binder. In RPC Binder, this is redefined as RPC session talking over RPC transport. And we can have different transports implemented for different kinds of communication mechanisms. So the first implementation of this is POSIX sockets. And right now, RPC Binder supports the INET, Unix, and VSOC address families. So it's your TCP/IP, Unix domain sockets, and virtual sockets from the server world. The way that this is initiated is that one client doesn't need to, we use the terminology of a server, but it doesn't need to be a server. One endpoint starts RPC server and listens for new connections. The other client connects to it with the RPC session class. And once they've established that connection, they can, each one of them can provide our binder objects to the other. So when the session is established, each endpoint dynamically spawns new threads to handle the incoming RPC connections up to a configurable maximum. So there's a maximum number of threads that can be spawned, but unlike the regular binder, these are spawned dynamically on demand. And the session ends with one endpoint calling RPC session shutdown, which interrupts all the threads and closes all the connections. What needs to change compared to the regular kernel binder is that now the object management logic cannot live in the kernel anymore, and it needs to be moved into user space. So with RPC Binder, that libbinder shared library is also doing the reference counting on the side of the object owner. And def notifications are either sent by the owner when the ref count of an object drops down to 0, or if the other endpoint closes the connection, if there's a hang up or a timeout. Another piece of functionality supported by RPC Binder is TLS-based authentication and encryption. All right, so now you can be talking over TCP/IP connection. That shouldn't be happening in plain text. So RPC Binder supports a TLS-style connection. Authentication can be done in either direction. You could have just the the server authenticating to the client, or just the client authenticating to the server, or in both directions. And this is completely configurable either by specifying a list of trusted certificates or specifying a list of roots of trust. This is initialized by constructing either your RPC server or your RPC session with a different kind of RPC transport context factory, this one having the suffix TLS. And finally, RPC Binder has a versioned wire format. So that's a big departure from the regular binder. There hasn't been a stable release yet, but the protocol itself is ready for versioning. So once we get more comfortable with the state of the wire format, at some point there's going to be a 1.0 release, and the wire format will be stabilized. Okay, so the differences from the regular traditional kernel binder. First of all, only some of the address families support passing file descriptors. So for example, the Unix domain sockets do support this. You can just pass FDs the same way you would with regular binder, but your TCP and VSOC do not. So you need to find other ways how to share files between processes if they're not running on top of the same kernel. And we do have one potential solution to that, which I'll mention in a slide later on. There's also no global object namespace, right? So this kernel binder keeps track of all the objects that have been shared over binder across the whole system. But with RPC Binder, you're only creating a connection between two endpoints, and that creates a local object namespace that's only shared between those two endpoints and nobody else. So one thing that you can do with kernel binder, but not RPC Binder, is taking an object from client A, giving the handle to client B, and client B passing that same handle to client C. That's not possible with RPC Binder. You also can't use the get calling bit and get calling UID functions, because that depends on the kernel telling you who's on the other side of your binder connection. That's not possible with sockets. And finally, you don't get the explicit scheduler hint. So there's no reason why kernels couldn't optimize something like sending a message over UDS and giving a scheduler hint that way. But RPC Binder, because it's only in user space, doesn't have an option of doing that itself. And the last kind of weirdness of RPC Binder is that weak pointers cannot be promoted to strong pointers once the ref count drops to 0. In the kernel binder, even if you only have a weak pointer to something, until it's garbage collected, you might be able to promote it back to strong. But with RPC Binder, that's not possible. All right, moving on. So I chickened out, and I'm not going to do a live demo, but we have a recording of one of our engineers playing with RPC Binder. And just to give you an idea of what's possible with this, even if it's not directly useful, he has two phones in his hand, and he's going to be controlling the brightness of one of them on the right-hand side. It's going to moving the progress bar there. But the brightness synchronizer class has been modified to, instead of connecting to the display manager on the phone, it's on the local phone, to connect over the network to the display manager of the phone on the left-hand side. So if we play this video, you can see that he's controlling the brightness on one phone, and it's actually controlling the brightness of the phone on the left-hand side. And this was implemented with basically something like 10 lines of code, where instead of instead of talking to the service manager to find the display manager locally, the left-hand phone exposes a server on a given port, and brightness synchronizer connects to it. On the right-hand side, the interfaces are exactly the same, but you get a binder connection between two different devices. Okay. Oh, this is playing again. There we go. So going to use cases. RPC Binder as a project existed for a while, which never had a real need to take it to production. That real need came with the Android Virtualization Framework, which is the team that I'm on. And in AVF AVF allows you to take a part of your application and execute it inside a virtual machine, which is isolated from the rest of the system. So you have your regular Android OS, you have your application, and you can start this virt manager process, which will spawn a new VM on the right-hand side and load a part of your application inside that VM. And this can be useful if you're doing sensitive operations where you're worried about another application in Android, maybe leveraging a vulnerability in the Linux kernel and snooping on your computation. You can offload that to an isolated environment. So in this case, we're not running on top of the same kernel. There are different kernels. There's the GKI Google kernel image and the microdroid kernel. They're completely separate. And they can communicate over VSOC, virtual sockets. So in this case, if we want to have the application, the real application, talk to the small portion of itself that's running inside the VM, and the only communication mechanism is VSOC. So in this case, we needed, our goal was to make this as seamless as possible, right? You already have an Android application. You want to split it up, which means, take your existing classes where you already have an interface defined between them and just offload part of them to a VM. So we wanted AIDL running on top of VSOC, which is why we went to the offer of RPC Binder and helped them productionize this as part of AOSP. So where we are today is that the application-to-application communication is RPC Binder. We also have the virtualization manager talking to microdroid manager over RPC Binder. We've gone further than that. The application inside the VM, when it's talking to the microdroid manager for the services available inside the VM, it's not actually using kernel binder as it could. It's actually using RPC Binder over Unix domain sockets. And that allowed us to completely remove the kernel binder from the microdroid kernel and save a few megabytes of both disk space and RAM space at runtime. And we also use RPC Binder over UDS when this application is talking to the virtualization manager, because this is just a sub-process of the application running in a different SELinux domain, and setting up kernel binder dynamically like this is quite complicated. So this is basically using UDS as a pipe between the two processes and setting up RPC binder with a rich AIDL interface between them. And at the same time, these processes can continue using regular binder. So the Virt manager process is talking to virtualization service, which is a global resource allocation service for virtualization, and that's using the regular kernel binder. And the application can continue using kernel binder for talking to system services as before. So you can mix and match. This microdroid manager is also talking to two different clients over RPC binder, once over UDS, once over VSOC, and it's all working in its own kind of local namespace just fine. So for virtualization, we also needed to share files because we have use cases where we compile the system jars inside a VM. And for that, we've built a small Fuse-based remote file system, which has FS-Verity integrated into it. And it's using communication over RPC binder over VSOC. So it's just running inside microdroid kind of as a service to the application. And it's communicating with a file server on the big Android side and exposing files as a Fuse mount point inside microdroid. This is currently a separate project, but at some point those two might be merged as a way how to share files with RPC binder over arbitrary connections. RPC binder since then has found more users. For example, it's already implemented in Trusty, where Trusty is the reference trusted execution environment operating system for TrustZone. And Trusty, when it's talking between Linux and the trusted applets, it's using the TIPSY communication protocol, which is similar to UDS, but it's designed for use across clusters. And the thing with TIPSY is that it's used to implement the backend of your vendor HALs. So Android talks to the HAL over AIDL, and the HAL needs to translate that request over TIPSY to this trusted applet. So in the past there was just a custom protocol, but now we can actually in the HAL just proxy the kernel binder request over RPC binder straight to Trusty. Maybe someday we could just skip this proxy completely, basically have the Android endpoint talk to Trusty over RPC binder directly, but that might take a while. One benefit of that is that it would also make these services reachable from VMs, whereas today you need to go via the main OS if you wanna reach these trusted services. And finally, we have other ideas where RPC binder can be used, even though none of them are actually implemented at this point. It can be useful for testing because running anything on Android, building Android OS just takes forever. It's so much easier if you can just test things on a PC. So all of testing happens on host, which is the term used for the PC. And if you're testing on host, you can actually start testing your AIDL with RPC binder, because RPC binder can be compiled for any Linux, even without Bionic. And it can also be compiled for more exotic operating systems, like we've seen with Trusty, right? Porting to Trusty required a very small amount of work, implementing a custom transport and making binder work single-threaded. But all of that work's been done now. so it can scale to other operating system as well. And one example of how you can start testing things with RPC Binder is this function called create RPC delegate service manager, which you can find in AOSP. And it creates a proxy from your host PC to the service manager running on a device connected over ADB. So ADB supports TCP/IP over ADB, and we can now run RPC Binder on top of that. It allows you to connect directly to the service manager of your device, and you can start probing it from your PC. So, for example, you can build a component that requires the service manager, but you don't need to rebuild Android every time you want to test it. You can just test it on the host and connect it to the service manager. And RPC Binder can also be useful for communication between multiple Android devices, like multiple devices in your home. And it can be useful for communicating with Android deployed on a network. So, for example, Android running in the cloud or Android running in a vehicle. But again, those are just ideas. None of that is shipping today. But we think that this is a useful mechanism, and we want to continue developing it going forward. So that's all I have. Thank you very much. If you're interested in this topic, you can find the source code by running this command in your AOSP tree, go mod binder RPC test. It will just take you to the folder where that is defined, and you can run the tests with a test binder RPC test. And this is actually a really good example of a very nice piece of source code where you can see how RPC Binder is set up and how to use it in your own project. And if you're interested in this, send me an email. My email address is at the beginning of the slides, and we can discuss if RPC Binder would be useful for your use case as well. Now I'm happy to take any questions. I think we have a few minutes left.
Yeah, sure. Does anybody have any questions for David? I've got a few.
Yeah, I have a question about the Trusty work. Do you know if anybody's already doing similar work that you guys did for Trusty for Opti?
You mean for RPC Binder? I don't think so.
Okay.
But I guess somebody at Linaro could do that.
Yep.
Yeah, I also have a question. So you mentioned that the RPC Binder does not support getting caller PID UID. So how do permissions work then? So how do you protect the calls? No?
I mean, that's why you wouldn't just replace kernel binder one-to-one. You can use TLS for authenticating the other endpoint. You can base your permissions on that if you want to. In some other situations, you might be able to infer the UID from other means. For example, the setup where the application talks to Virt Manager, because it's a child, it actually knows the UID of the parent and its PID as well. So it can, it's running in a different SUNIX domain, more privileged than its parent. So it can make decisions based on that. But yeah, there is no silver bullet here.
One question from me. Hi, David. For the communication between devices, were you using gRPC behind the scenes, or how does that work?
No, this is really serializing the binder protocol over a socket connection.
Okay, thank you.
Hi, David.
Hi.
I'm interesting about the virtualization part. Actually, I am working in using a new system based in Trout that Google already implemented and deployed on the website. So I'm asking just about specific use case that sharing a sensor or like a physical driver, for example, Bluetooth or Wi-Fi using the gRPC is possible for this use case?
I mean, you can proxy the requests over such a protocol to a VM that owns that particular hardware, right? That's possible. It wouldn't give you direct access to that hardware.
Yeah, actually, in official website of Google, they mentioned that using the Virtual console may be a solution, but I can see that gRPC is well used, for example, in the ADB, and there is also in the host side, like gRPC server running. And for more detail, I using the cross VM like virtual machine, and the KVM like the hypervisor, and the host is also Android, and the guest is another Android site based in Trout. But I still like using the sharing the device, the hardware device like Bluetooth or sensors like location. And specifically for the location and GNSS, I can see some client and service gRPC, but I still confused about using, for example, the virtual devices side by side with gRPC. It is possible or not?
gRPC will be running on top of one of the virtual devices, right? Typically VSOC. Yeah. That's the actual message exchange mechanism between, like the memory sharing mechanism between the two virtual machines, right? And you build your communication protocol on top of that shared memory. So yeah, they're not side by side; they're one on top of the other.
Oh yeah.
But I'm not familiar with how if there's a gRPC protocol for accessing Bluetooth, there might be, but I'm not aware of it.
Yeah. Nice, thank you.
So David, can I just clarify a little bit then? So is this actually being used in production systems now, or is this something that's on master and is likely to be in Android 14? What's the current state of this?
So this has already shipped in Android 13 on Pixels, at least. And it's being extended in Android 14. Like I said, there's the wire protocol hasn't been stabilized yet. So you can't mix and match different releases of the binder library. But as long as you're updating things atomically, then it works fine.
Cool. And kind of, I guess, a follow-on from what Ahmed was just saying, that is it just a crazy thing? Can I use this to proxy my HAL to a different machine? So I can actually have a different machine running my HAL and then use the binder RPC to connect the two together.
So you can already do that, right? It's something like Cuttlefish already implements the HALs outside of the main OS itself.
Good point. Yeah.
RPC Binder makes it a lot easier because now you can just proxy the whole AIDL interface all the way out.
Yeah.
I
mean, I don't know why I would want to do that, but I'm sure there are reasons.
Something like Chrome OS has this kind of setup. If you're running Android as one of the VMs, then that's exactly what you're doing.
Yeah.
You don't need a custom protocol to extract that communication out.
Okay. Anyone else have any questions? Otherwise, I'll bring this to an end.